14 stars dance together in a single, impossible system. This is a Quattuordecuple star system, a cosmic family of 14 suns bound by gravity. By the end of this journey, you will know 30 of the most bizarre truths scientists have uncovered about these celestial giants. We will explore how planets might struggle to exist there and why these systems could be factories for stellar collisions. What part of this 14-star reality feels the most alien to you? The very first discovery shatters any illusion of cosmic harmony. These 14-star systems are not serene families but chaotic, gravitational battlegrounds. With so many massive bodies pulling on each other, stable orbits are a fleeting dream. Predicting where a single star will be in 1,000 years is a task that defies even our most powerful supercomputers. Instead of a predictable dance, these systems are defined by a deep, inherent instability. They are temporary crucibles of cosmic evolution destined for a violent end. When you run simulations of these systems, the results are breathtakingly destructive. Stars do not simply orbit one another. They slingshot past each other, trading gravitational energy in a frantic game of celestial chicken. One star might gain so much speed it is violently flung from the family entirely, cast out into the dark interstellar void to wander alone. Other times, the paths of two stars intersect, leading to a catastrophic merger. Imagine two suns, each with its own immense gravity, crashing together in a titanic collision that forges a new, more massive star in a flash of unimaginable energy. These systems are not timeless monuments. They are transient, fiery spectacles offering a front-row seat to the most dramatic stellar events in the universe. What does such chaos mean for the possibility of planets, or for the very stars that call this gravitational maelstrom home? This gravitational chaos makes the very idea of a stable planet seem almost laughable. Any world forming here would be sentenced to an orbital roller coaster of epic proportions. Its path around one star would be constantly tugged and warped by the gravity of the other 13. Imagine a single planet not tracing a neat circle but instead whipping through a tangled, chaotic path. It might swing close to one star, feeling blistering heat, only to be flung out into the frigid darkness near the edge of the system. Its sky would be a constantly shifting canvas of suns. Some days, 3 or 4 different stars might hang overhead, casting complex, shifting shadows. Other times, the planet could be left in total darkness for years, all its suns clustered on the opposite side of the system. The very rhythm of day and night, the foundation of life on Earth, would be utterly meaningless here. The concept of a habitable zone, that just right region where liquid water could exist, completely breaks down. In a 14-star system, the habitable zone is not a placid ring. It is a shimmering, chaotic volume of space that writhes and shifts with every gravitational pull from the dancing stars. A planet might pass through this comfortable region for only a brief, fleeting moment before being hurled back into a deep freeze or scorched by a close stellar path. Life as we understand it, requiring stability and time to evolve, would find this environment impossibly hostile. The existence of a planet here is not a promise of a home, but a spectacle of celestial violence, a world on a wild ride with no safe way off. This internal stellar heating creates stars that defy simple classification. We usually assume a star's temperature and activity are determined solely by its mass and age. But in these dense systems, that rulebook is torn apart. A star that should be relatively calm and stable based on its size can instead be boiling with unexpected fury. Its surface might be scarred by sunspots, and its atmosphere could erupt with flares far more powerful than our sun's most violent outbursts. This is stellar hyperactivity, a direct result of being constantly stretched and squeezed by its many siblings. It is like comparing the volcanic moon Io to our own placid moon. Jupiter's gravity constantly needs Io, heating its interior to the point where it becomes the most volcanically active body in our entire solar system. Now amplify that effect from a planet-moon relationship to a star-star relationship. The forces involved are astronomically greater. Instead of a small moon being heated, we have an entire sun, a massive ball of plasma, being internally agitated. This means the star does not just shine from nuclear fusion in its core. It also glows with this added gravitational energy, making it anomalously bright and violently unpredictable. A star's life in this system is one of constant, stressful exertion, forever heated from the outside in. This chaotic hyperactivity leads directly to one of astronomy's greatest mysteries. How could such a complex and unstable family of 14 stars possibly come together in the first place? The leading theory, known as hierarchical fragmentation, paints a picture of a stellar birth more turbulent than any we can easily comprehend. Imagine a single colossal cloud of gas and dust, one so massive it could form a small star cluster. As this cloud begins to collapse under its own immense weight, it doesn't just shrink into one dense core. Instead, it shatters, it breaks apart into several large, unstable chunks. But in the case of a Quattuordecuple system, the process doesn't stop there. Each of those large chunks is itself so massive and turbulent that it fragments again, and then those fragments might even break apart one more time. It is a cascade of creation, a cosmic Russian nesting doll where every piece contains the seeds of more stars. This process requires conditions that are almost unimaginably extreme. The original gas cloud must have been incredibly dense and spinning rapidly, filled with supersonic turbulence that rips it into a specific multi-layered architecture. The resulting system isn't a random swarm of 14 stars. It is organized into a hierarchy of orbits. You might have 2 stars in a tight binary, locked in a close embrace. That binary pair then orbits a third star, forming a triple system. That triple system, in turn, could be part of a wider orbit with another pair of stars, and so on, building up a dizzying ladder of gravitational relationships until 14 stars are all bound together. A 14-star system pushes this hierarchical model to its absolute breaking point. It suggests a birthplace of staggering density and violence, a stellar nursery where the forces of collapse and fragmentation operated on an overdrive we rarely see in the cosmos. This isn't just a cloud giving birth to stars. It is a cloud exploding into a complex, multi-generational family in one frantic, epic event. The sheer number of stars implies a level of initial turmoil that challenges our very understanding of star formation. If this is how these giants are born, what incredible events mark their final days? The violent past of these 14 star systems is written across our galaxy in the form of runaway stars. These are solitary suns rocketing through interstellar space at speeds so immense they are effectively escaping the Milky Way. For a long time, their origin was a cosmic puzzle. How does a single star get catapulted to such velocities? The answer appears to lie in the gravitational chaos of systems just like the one we are exploring. Many of these lone wolf stars are likely the casualties of celestial breakups, violently evicted from their crowded stellar families. The mechanism is a gravitational slingshot. In a system with 14 stars constantly interacting, close passes are inevitable. When 2 stars swing near each other, their gravitational fields can act like a catapult. One star might absorb the energy of the encounter, slowing down and sinking deeper into the system's core. The other can be flung outward with such ferocious speed that it breaks free of the system's gravitational grip entirely. It is a stellar ejection, a permanent exile into the galactic void. This discovery transforms our understanding of these runaway stars. They are not born in isolation. They are the refugees of gravitational wars, their incredible speed serving as a permanent record of a violent expulsion that happened millions of years ago. Every one we detect is a powerful, if indirect, piece of evidence that ultra-multiple systems are indeed these turbulent, unstable places we theorize. constantly shedding members through chaotic interactions. The galaxy is littered with these cosmic outcasts, each one a ghostly echo of a family that could not hold itself together. Unraveling the identities of these 14 stars presents a unique nightmare for astronomers. The primary tool for understanding a star is its spectrum, the fingerprint of light that reveals its temperature, composition, and age. But in a quattuordecuple system, you do not get 14 clean fingerprints. Instead, you get a single, impossibly messy smear of light. The light from a hot, blue, massive star blends with the glow from a cool, red, elderly star and everything in between. It is like trying to identify every instrument in a symphony by listening to a single, deafening chord played by the entire orchestra at once. The resulting data is a tangled web of overlapping signals, a cryptographic puzzle written in the language of physics. This blending makes simple classification almost useless. You cannot just point a telescope and say, that is a type G star like our Sun. The data you see is the average of 14 different stars, a phantom that does not actually exist. The true nature of the system is hidden, buried under layers of combined starlight. To solve this, scientists must become cosmic detectives, employing sophisticated computer models to virtually disentangle the single blended spectrum back into its 14 individual components. They search for subtle, telltale shifts in the light-minute signatures that betray the presence of a specific type of star. This painstaking process often leads to shocking revelations. What appeared from the blended light to be a system of fairly similar stars might, upon closer analysis, contain a stellar corpse. A white dwarf, the dense, Earth-sized remnant of a dead sun, could be hiding in the data, its faint light almost completely washed out by its brilliant siblings. Even more dramatic is the occasional discovery of a massive O-type star. These are the titans of the stellar world, blazing with such ferocious heat and brightness that they live fast and die young. Finding one in a 14-star system is like discovering a caged hurricane. Its intense ultraviolet radiation would be sterilizing entire swaths of the system, utterly dominating the environment and drastically shortening the lives of the stars around it. These spectral ghosts force us to accept that the true character of these systems is never what it first appears. The surface chaos is merely a veil, hiding even deeper and more extreme stellar personalities waiting to be discovered. This cosmic detective work uncovers one of the most puzzling truths about these systems. Not all 14 of these stellar siblings were necessarily born together. Astronomers have found that some members of a quattuordecuple family can be millions of years younger than their companions. This age disparity shatters a fundamental assumption of stellar astronomy, the idea that all stars in a gravitationally bound system form from the same cloud at roughly the same time. How can a family of stars so intimately linked by gravity have such different birthdays? One startling possibility is stellar capture. The chaotic, dense environment where these systems live often puts them near other young stars in a cluster. As the 14-star system plows through this stellar nursery, its immense collective gravity can act like a net, snatching a younger, wandering star that drifted too close. This captured star, born from a different part of the cloud millions of years later, is then gravitationally shackled to the existing older family. It becomes an adopted sibling, forever bound to stars that are its elders. Another scenario involves the original birth cloud itself. The process of hierarchical fragmentation is not always instantaneous. While the core of the cloud collapses quickly to form the first stars, pockets of gas on the outskirts might remain unstable for a longer period. These delayed fragments could finally collapse and ignite into new stars millions of years after their sisters were born. Imagine a single, massive stellar nursery where the first stars light up, and then, eons later in cosmic terms, a final burst of star formation occurs in a far-flung pocket of the same structure. The result is a single, bound system with two distinct generations of stars. This has profound implications. An older star in the system might be well on its way to becoming a red giant, expanding and threatening its neighbors, while a much younger star is still in its fiery infancy. The dynamics of such a mixed-age family are even more complex and unpredictable. It means these systems are not just chaotic in their orbits, but also in their very origins, built through a patchwork process of birth and adoption over vast stretches of time. The chaotic origins of these stellar families extend to the very cradles of planets. Within a 14-star system, it is not just the suns that are locked in a gravitational struggle. The raw material for new worlds is also caught in the fray. We find multiple circumstellar disks, vast, flat rings of gas and dust, each one swirling around a different star. These are the nurseries where planets are born, but here their peace is shattered. The gravitational pull from neighboring stars constantly tugs at these disks, shearing their edges and truncating them. A disk that, in isolation, might have stretched for billions of miles is instead chopped short, its potential for planet formation severely limited. The disks do not simply ignore each other. Their outer fringes can interact, pulling at one another, warping, and even exchanging material in a slow-motion celestial trade. Picture several glowing rings of dust, each orbiting its own star, but their edges intersecting and distorting like ripples from stones thrown too close together in a pond. This creates an environment where planet formation becomes a battle against constant disruption. A young, growing planetesimal, a building block of a world, faces a perilous existence. It must coalesce from dust while being gravitationally jostled not only by its parent star but by a dozen others. Its path through the disk is no smooth journey. A close pass from another star can send shockwaves through the disk, scattering forming planets or hurling them into chaotic orbits that lead to certain destruction. The very act of world building here is an exercise in cosmic resilience, a desperate attempt to assemble order from a storm of gravitational noise. For a planet to survive here, it must form quickly and find a stable niche before the shifting tides of gravity tear its cradle apart. The sheer density of a 14-star family makes stellar collisions not a question of if, but when. With so many massive bodies hurtling through a confined space, gravitational nudges constantly tighten their orbits, setting the stage for the ultimate cosmic catastrophe. A direct collision between two suns is an event of almost incomprehensible power. When two stars merge, their immense gravitational potential energy is released in a single, cataclysmic flash. This collision would unleash a supernova-like explosion, a fireball of radiation and matter that could, for a few fleeting weeks, outshine every star in its host galaxy combined. It is a temporary new sun born from the violent death of two others. The aftermath of such an event would permanently reshape the system. The colliding stars would forge a single, new and more massive star, its composition a scrambled mix of its progenitors. Alternatively, if the stars were of the right types, the collision could create a bizarre stellar remnant, like a blue straggler, a star that appears unnaturally young and hot for its environment. The fingerprints of these ancient collisions can still be found. Astronomers sometimes detect stars with highly unusual chemical signatures, surfaces rich with elements that should have sunk deep into the stellar core. One compelling explanation is that these stars are the survivors of a past merger, their outer layers polluted by the debris of a companion they consumed. In a Quattuordecuple system, this violent recycling could be a common part of the life cycle, a brutal method of stellar renewal that seeds the system with the heavy elements needed for new planets and perhaps one day for life itself. This relentless chaos might be the forge that builds entire moons. The same gravitational turbulence that tears these systems apart could also be a prolific creator of new worlds on a scale we are only beginning to appreciate. Consider the leading theory for the origin of our own moon. Billions of years ago, a Mars-sized protoplanet named Theia is thought to have collided with the young Earth. The Titanic impact blasted a ring of molten debris into orbit, which later coalesced into the moon we see today. For our solitary solar system, this was likely a rare, catastrophic fluke. But within a quattuordecuple star system, such moon-forming collisions may not be rare at all. They could be a standard part of planetary evolution. The gravitational nudges from 14 stars would constantly stir the pot of planetary formation. A protoplanet the size of Theia, peacefully orbiting its parent star, could be repeatedly yanked by the gravity of a passing stellar sibling. Each tug would warp its orbit, shifting its path ever so slightly until, after thousands of years, its new trajectory sends it on a direct collision course with another large world. In this environment, giant impacts are not accidents. They are an inevitable consequence of the gravitational environment, a frequent and violent method of planetary construction. Imagine not just one moon-forming event in a system's history, but several. A single system could be littered with the remnants of these ancient crashes, a graveyard of shattered worlds and a collection of newly forged moons orbiting surviving planets. This transforms our understanding of these chaotic places. They are not just destructive, they are also creative, acting as cosmic factories for exotic planetary systems that would never form in the calm of a single star system like our own. The very forces that make these systems so hostile to life as we know it might also be the very same forces that build the most spectacular and complex planetary architectures in the galaxy. This gravitational chaos can flip entire orbits upside down. Amidst the 14-star dance, astronomers have detected a stunning anomaly. Some of the stars or the large planets that might orbit them are moving in retrograde. They travel in the exact opposite direction to the system's overall spin. Imagine a single gear in a vast, intricate clockwork suddenly reversing its rotation, spinning backwards against the flow of everything else. This is not a minor quirk, it is a fundamental violation of the standard model of how star systems form. When a system is born from a single, spinning cloud of gas and dust, conservation of angular momentum dictates that everything should spin and orbit in the same general direction, just like the planets in our own solar system. A retrograde orbit is a cosmic scar, a permanent record of a violent intrusion. The most likely explanation is a capture event. An object, either a lone star or a massive planet, was wandering through interstellar space when it passed too close to the 14-star family. The system's immense gravity reached out and seized it, but this was not a gentle capture. The object likely made a complex, close pass with one or more of the system's stars, a gravitational interaction so intense that it robbed the object of its original momentum and flung it into a new, stable orbit that just happens to be backwards. This captured object is now a permanent member of the family, but it is a rebel, a constant reminder that this system's history is written in collisions and theft. Its backwards path adds a layer of profound dynamical complexity, creating gravitational resonances and instabilities that would be entirely absent in a well-ordered system. Every time astronomers detect a retrograde orbit, they are looking at the ghost of a long-ago celestial kidnapping, a permanent monument to the day this chaotic system reached out and stole a sun from the void. The magnetic chaos within such a system generates stellar tantrums of cosmic proportions. With 14 stars orbiting so closely, their powerful magnetic fields do not simply exist in isolation. They constantly tangle, snap, and reconnect with each other. This magnetic mayhem acts as a colossal particle accelerator, channeling vast amounts of energy and hurling it into space in the form of stellar flares. But these are not like the solar flares we occasionally see from our sun. These are superflares, eruptions that can be thousands, even millions of times more powerful. A single one of these events would unleash as much energy in minutes as our entire civilization would use in billions of years. For any hypothetical world forming in this system, these flares are not a spectacle. They are an existential threat, A superflare would hit a planet like a physical wave of radiation, stripping away its atmosphere in an instant. It would scorch the surface, boiling away oceans and baking the rock into a global sheet of glass. The intense X-rays and ultraviolet light would shatter any complex molecules that might be the precursors to life, and this sterilization would not be a one-time event. It would be a recurring, random apocalypse because the magnetic interactions between the stars are so complex and chaotic. These superflares can erupt without warning at any time. A planet could enjoy 1 billion years of relative calm, only to have its biosphere utterly erased by a single, unpredictable eruption from a star halfway across the system. The very idea of a stable, evolving biosphere becomes a cruel joke. Life here would not be a gentle candle flame, but a spark in a hurricane, snuffed out over and over again before it ever had a chance to truly catch hold. The magnetic storms are just one expression of the immense energies at play. Beneath the light shows and the stellar tantrums, a deeper, more fundamental vibration is being generated. This entire 14-star system is a factory for gravitational waves. Every single one of those 14 massive bodies, as it whips through its complex orbit, is shaking the very fabric of spacetime. According to Einstein's theory of general relativity, any accelerating mass creates ripples in spacetime, and in a system this dense and chaotic, the acceleration is relentless. The result is a persistent, complex hum, a symphony of spacetime vibrations emanating from this cosmic maelstrom. For now, this hum is too faint for our current detectors to hear. But the next generation of observatories, like the planned space-based Laser Interferometer Space Antenna, or LISA, is being built to listen. LISA will consist of 3 spacecraft flying in a giant triangle millions of miles across, using lasers to measure the microscopic stretching and squeezing of space itself. A Quattuordecuple star system would be a prime target, a celestial orchestra playing a tune written in gravity. Detecting this gravitational wave signal would be a revolution in astronomy. It would provide a completely new sense with which to study these systems. Light can be blocked or distorted, but gravitational waves pass through almost everything unimpeded. By listening to the specific frequencies and patterns in the hum, scientists could literally hear the orbits. They could determine the exact masses of stars that are otherwise hidden in the blended light. They could sense the subtle, processing dance of a tight inner binary, or even detect the final, inspiraling merger of 2 stars as a crescendo in the signal. This is not just observing the system, it is taking its pulse, feeling the rhythmic heartbeat of gravity itself. The chaotic dance of 14 stars is not just a visual spectacle. It is a source of the universe's most fundamental music, a song of pure gravity waiting to be heard. This constant gravitational churning fills the space between the stars with a haze of destruction. Unlike the relatively empty voids of our solar system, the environment within a Quattuordecuple family is a dense fog of dust, rock, and ice. Every close stellar pass acts like a colossal stirrer, churning up the primordial debris left over from the system's formation. Asteroids and comets that would otherwise be locked in stable, distant orbits are constantly being shaken loose, sent careening on new, dangerous trajectories through the inner stellar domains. For any world trying to exist here, the sky is not a serene expanse. It is a perpetual shooting gallery. The planet's surface would be under a near-constant barrage. Impact flashes would light up the horizon day and night as mountain-sized rocks, accelerated by stellar gravity, slam into the crust at phenomenal speeds. There would be no calm periods, no long stretches of geological peace. The planet would be geologically active in the most violent sense, its surface continuously remade by fire and force. This is not like the occasional meteor shower we experience on Earth. This is a permanent, existential meteor storm. The very air would be thick with dust, casting a perpetual, dim twilight even when multiple suns are in the sky, and the ground would shake with the drumbeat of extinction-level events happening not every 100 million years, but perhaps every few centuries. Life could never gain a foothold, just as a fragile sapling cannot grow in a forest constantly raked by machine gun fire. No complex ecosystem could evolve while the very ground beneath it is being systematically pulverized. The system itself becomes its own executioner, using the leftover shrapnel from its birth to ensure that nothing within it ever finds peace. 15 stars, not 14. This is the strange arithmetic of the prisoner star. While 14 stars engage in their frantic dance at the system's heart, a 15th may exist in a state of profound isolation, locked into an orbit so impossibly wide it defies human comprehension. This star is a ghostly warden, a distant sentinel bound by the faintest whisper of gravity. A single orbit could take millions of years to complete, a timescale that dwarfs all of human civilization. For almost its entire unimaginably long journey, this star would appear as just another faint point of light in the cosmic darkness, utterly disconnected from the violent ballet at the center. Its environment would be one of near-total silence and cold, a perpetual interstellar night. Yet, despite this vast separation, it is not free. It is a permanent prisoner of the system's collective gravity, forever tethered to a family it barely knows. Its existence reveals a new layer to the system's hierarchy, a gravitational reach far more extensive than the chaotic core would suggest. This star lives a dual life. For millennia at a time, it experiences the solitude of deep space, a solitary sun drifting in the void. But the physics is inescapable. At the far point of its elliptical orbit, its velocity slows to a crawl, and the system's gravity begins to pull it back. It begins its long fall inward, a multi-million-year descent towards the nest of stars it calls home. This is not a safe homecoming. As it finally swings through the inner system, its passage would be a moment of supreme gravitational tension. Its gravity, though weak from such a distance, would still tug at the 14 inner stars, adding one more unpredictable variable to their already chaotic dance. It could nudge one star just enough to trigger a cascade of instability, or it could itself be captured into a tighter, more dangerous orbit by a close pass. The prisoner star is a time bomb on a galactic clock, its rare visits potentially heralding epochs of renewed chaos and destruction for the entire family. Within this stellar chaos, the very nature of light and color is torn apart. Forget a single yellow sun like our own. The sky of a 14-star system is a disorienting canvas painted with every color of the stellar rainbow. Fierce blue-white giants blaze with the heat of a forge, while cooler, orange dwarfs glow like cosmic embers. Between them, yellow suns similar to our own would appear almost insignificant. This is not a sky with a primary star. It is a sky dominated by a committee of suns, each one vying for attention and casting its own distinct hue. The idea of a single light source, a single direction for shadows, is completely erased. On the surface of a planet, your shadow would not be a single, dark shape. It would be a fractured, multicolored mess. As the stars move in their complex dance, you might cast 3 or 4 separate shadows, each one a different shade of blue, yellow, and red, all shifting and stretching in different directions. The very concept of color itself would be untrustworthy. An object that appears pure white under the harsh glare of a blue giant might look deep crimson when an orange star rises, making visual reality a fluid and unpredictable experience. There is no true night, only a perpetual, shifting twilight. Even when most stars are below the horizon, at least 2 or 3 would likely still be above, ensuring that darkness as we know it is a forgotten luxury. The rhythm of life would be dictated not by a single sun, but by the ever-changing symphony of light from 14 different ones, a constant, beautiful, and utterly bewildering cacophony. The simple, elegant clockwork of our solar system is a cosmic lie. For centuries, we have relied on Kepler's laws of planetary motion, a set of beautiful mathematical rules that describe how a planet traces a predictable ellipse around its single sun. These laws are the bedrock of classical astronomy, allowing us to calculate orbits with pinpoint precision for thousands of years into the future. But place those same laws into a Quattuordecuple star system, and they shatter into utter uselessness. The problem is not with the laws themselves, but with their fundamental assumption of a simple two-body dance. Kepler's perfect ellipses depend on a single, dominant source of gravity. In a system with 14 massive stars, you do not have one sun. You have 14 separate, competing gravitational centers, each one pulling on all the others in a constantly shifting tug of war. An object's path is not a clean curve around one star. It is a tortured, unpredictable trajectory, jerked and warped by a dozen different masters vying for control. The motion becomes fundamentally chaotic. This is not just complex, it is chaotically unpredictable in the strict mathematical sense. The slightest, most immeasurable difference in a star's starting position or velocity, a shift smaller than the width of an atom, will lead to a completely different configuration of the entire system given enough time. Run a computer simulation of this system twice with virtually identical starting conditions, and within a few thousand orbital cycles, the two versions will look nothing alike. One might show a stable configuration while the other ends with a star being ejected into deep space. This is the famous butterfly effect, but on a stellar scale. The flap of a butterfly's wings on a hypothetical planet could, in theory, set in motion a chain of gravitational perturbations that ultimately decides which star gets flung from the family a million years later. This profound chaos makes any long-term prediction an exercise in futility. We cannot say where any single star in this system will be in 10,000 years, let alone a million. The system's fate is not written in the stars, it is lost to a storm of gravitational noise. These 14 sun families exist in a class of their own, a realm where the clockwork universe breaks down and is replaced by a beautiful, terrifying, and fundamentally unpredictable dance. This stellar chaos is a forge for the universe's most extreme objects. The death of a single star in a 14-sun family is not a quiet, isolated event. It is a trigger for a chain reaction of cosmic destruction. When a massive star reaches the end of its life and explodes as a supernova, the blast is only the beginning of the catastrophe. The real danger lies in the shockwave, a spherical front of energy and high-velocity debris that expands outward at a significant fraction of the speed of light. In a normal, sparse star cluster, this wave would dissipate harmlessly into empty space. But here, it has multiple targets. This supernova shockwave can physically slam into the outer atmospheres of its nearby stellar siblings. The effect is like hitting a soap bubble with a sandblaster. The immense pressure can violently strip away the outer layers of a neighboring star, peeling it back to its core. A star that was destined to live for billions more years could be prematurely exposed, its life cycle abruptly and violently accelerated. In some cases, the sudden loss of mass and the intense compression from the blast wave might even induce a star that was not quite ready to go supernova to collapse prematurely. One stellar death can literally bully another into an early grave. The result of this domino effect is a gruesome stellar graveyard. After the fireworks subside, the system is left littered with the dense, dark remnants of its former members. We could see a collection of neutron stars, city-sized balls of degenerate matter so dense that a single teaspoon would weigh billions of tons, all whipping around each other in a tight space. Even more ominously, the most massive stars would leave behind black holes. This transforms the system from a chaotic dance of suns into a far more sinister dance of gravitational singularities. A small volume of space, once filled with light and heat, becomes dominated by invisible points of immense gravity, each one capable of trapping light itself. This is the ultimate legacy of such a crowded system. It begins as a brilliant, fiery family of 14 suns, but its inevitable end is a shadowy conclave of the dead, a final, silent state of unimaginable density and power. The light from this system is a broken clock. In a simple eclipsing binary, two stars pass in front of each other with metronomic regularity, causing predictable, repeating dips in brightness you could set your watch by. But with 14 suns, that clean, predictable rhythm disintegrates into pure noise. The combined light flickers and flares in a pattern so complex it appears utterly random. One moment, a faint red dwarf might transit a brilliant blue giant, causing a subtle, slow dimming. At the same instant, a third star on the other side of the system might unleash a massive flare, spiking the overall brightness. Before that flare even subsides, two other stars could begin to eclipse each other, their overlapping disks creating a bizarre, asymmetrical dip in the light curve. This is not one signal. It is a dozen different signals, all overlapping and interfering with each other in a chaotic symphony of light. For astronomers relying on photometry, the study of light intensity, this is an interpretive nightmare. Trying to decode this light curve is like trying to listen to 14 different songs playing at the same time from a single, broken speaker. You can hear the cacophony, but picking out the individual melodies, the distinct instruments, becomes an almost impossible task. There are no clean repeats, no dependable patterns to latch onto. The system's light becomes a cipher that resists all standard decoding, a permanent reminder that the serene clockwork of simpler systems is a cosmic fantasy here. This 14-star system might represent a natural ceiling for cosmic architecture. There appears to be a theoretical limit to how many stars can be bound together in a stable family, and quattuordecuple systems may be pushing directly against that boundary. The problem is one of escalating chaos. With each additional star you add to the system, you are not just adding one more gravitational partner. You are exponentially increasing the number of possible gravitational interactions, the close passes, the slingshot maneuvers, and the resonant instabilities. A system with 15 or 16 stars would be so profoundly unstable that it could not hold its shape for even a blink of cosmic time. The gravitational turmoil would tear it apart from the inside, flinging stars outward in a rapid-fire disintegration until only a smaller, more robust core remained. This is why finding a system with 14 stars is so extraordinarily rare. It is not a common configuration. It is a cosmic tightrope walk, a fleeting, precarious balance between immense gravitational binding and the inherent anarchy of so many massive bodies. We are not looking at a standard stellar family. We are witnessing a gravitational extreme, a system that has somehow managed to exist right at the edge of what physics allows. What we see is a temporary monument, a structure that has not yet crossed the line into immediate self-destruction. Its very existence gives us a critical data point, a glimpse into the maximum complexity the universe can sustain before its own laws demand a simpler, more violent arrangement. Even within this gravitational storm, pockets of impossible order can emerge. Deep inside the 14-star chaos, the tightest binary pairs create their own isolated worlds. Two stars locked in a close, frantic embrace can carve out a gravitational safe zone around them both. In this region, their combined gravity acts as a single, central point, and within that stable bubble, a planet could, in theory, form. This is a circumbinary planet, a world with two suns in its sky, but its reality is far more extreme than any fictional Tatooine. The planet would trace a wide, looping path around both stars, holding on for dear life at the very edge of their gravitational influence. Its orbit is a constant high-wire act, a delicate balance between being pulled apart by the two nearby stars and flung away by the gravity of the other 12. The planetary nursery itself, the disk of dust and gas from which this world would be born, faces constant assault. The gravitational tides from the binary pair stretch and compress the disk, heating it from the outside in. Yet, against all odds, planetesimals could coalesce. They would have to form quickly, clumping together before a passing stellar sibling shakes the entire disk apart. Finding a planet in such a location would be one of astronomy's greatest discoveries. It would be a testament to the raw, stubborn resilience of planet formation, proving that worlds can be born even in the most hostile and unforgiving corners of the universe. It suggests that life, against all probability, might still find a way to ignite in a sliver of calm within an endless hurricane. This constant exchange of violence and light writes its story directly into the stars themselves. Every star in this 14-sun family carries a chemical fingerprint, a record of elements forged in its own core and, surprisingly, in the hearts of its siblings. The space between them is far from empty. It is a bustling highway for stellar pollution, a chaotic mixing of elements that should never coexist in a single, isolated star. The primary delivery system is the stellar wind, a continuous stream of charged particles that flows from the surface of every star. In our solar system, the solar wind is a gentle breeze. Here it is a hurricane. A massive hot star might be blasting its surroundings with a wind so powerful it physically strips material from the atmosphere of a smaller, cooler neighbor. This star is not just shining on its companion, it is sandblasting it, forcing it to ingest a foreign cocktail of helium, carbon, and oxygen that it did not create itself. The result is a star with a contaminated surface, its outer layers artificially enriched with elements that tell a tale of a too-close relationship. This is a living record of stellar cannibalism, written in the language of atomic spectra. But the pollution can be even more extreme. Remember the chain reaction of supernova. When one of these titans explodes, it does more than just shock its neighbors. It hurls the very elements forged in its final moments out into the system at nearly the speed of light. This expanding shell of debris is rich with heavy elements like iron, silicon, and gold. As this supernova remnant sweeps through the system, it physically slams into the atmospheres of the other stars. A star that was born pure hydrogen and helium suddenly finds its surface dusted with atoms that were born in the heart of a dying sun. Imagine a young, yellow star. Its composition should be pristine and simple. Yet when we analyze its light, we find an unexpected overabundance of iron. This is not a mystery, it is a scar. That iron is the shrapnel from a stellar war, the ghost of a long-dead sibling that exploded and forcibly donated its innards to the survivors. These stars are not independent entities. They are communal creatures, sharing and stealing the very stuff of their being in a continuous, violent cycle of chemical enrichment. Their light tells a story not of solitary lives, but of a deeply interconnected and brutally shared history. The tightest binary stars in this system do not just orbit, they carve paths through warped space itself. Einstein's theory of general relativity, often a subtle effect elsewhere, becomes a dominant force here. For two stars whipping around each other at incredible speeds, the sheer strength of their gravity bends the fabric of space-time around them. This distortion manifests in a phenomenon called extreme orbital precession. The elliptical orbit of the stars does not stay fixed in space. Instead, the entire ellipse itself rapidly rotates, like a spirograph pattern spinning around its center. The point of closest approach, the periastron, shifts noticeably with every single orbit. In our solar system, Mercury's orbit precesses too, but at a glacial pace. Here, in a tight 14-star system, the precession can be so violent and fast that the orbit effectively paints a rosette pattern in the sky, completing a full rotation in just a few years instead of millennia. This is not a gentle drift, it is a frantic, visible wobble imposed by the geometry of the universe. These stellar pairs become a unique natural laboratory, a cosmic test bed for gravity under the most extreme conditions we can observe. The precise rate of this precession gives scientists a direct measurement of the system's total mass and the intensity of the gravitational field, data that is impossible to gather through light alone. Observing this effect confirms that Newton's simpler laws of gravity, perfect for our solar system, finally break down here. We are watching the universe play by Einstein's rules, where mass tells spacetime how to curve, and curved spacetime tells these stars how to move in their beautiful, mind-bending dance. The gravitational glue holding this 14-star system together is stretching our understanding of physics to its absolute limit. To keep 14 massive, chaotic suns from instantly flying apart requires a truly monstrous binding force, an anchor of almost inconceivable power. This leads to one of the most profound and unsettling possibilities in all of astronomy. What if the true center of this cosmic dance is not a star at all, but an emptiness of infinite density? The gravitational heart of the system could be a supermassive black hole. This is not the stellar mass black hole left by a dead star, but a behemoth, a primordial giant that could have formed in the early universe, a gravitational trapdoor sitting at the very core of this stellar family. In this scenario, the 14 stars are not merely orbiting each other. They are all collectively in a frantic dance around a common center of darkness. Their chaotic paths are not just the result of their mutual pulls, but are fundamentally shaped by the irresistible grip of this unseen master. This single idea would completely redefine what a quattuordecuple system actually is. It would no longer be a family of peers, but a stellar entourage serving a silent, gravitational king. The black hole would act as the ultimate stabilizer, its immense mass providing a fixed point that the stars revolve around, preventing the entire structure from disintegrating under its own internal chaos. Its gravity would be the cage that keeps these 14 furious suns from breaking free. Evidence for this is subtle but compelling. Astronomers would look for the telltale signs of stars orbiting an apparently empty point in space, their velocities revealing the presence of a mass far greater than any visible object could account for. They would search for the faint, telltale glow of an accretion disk, a swirling vortex of superheated gas and dust spiraling into the black hole's event horizon, a last whisper of light before being swallowed by the void. Finding such an anchor would solve the mystery of the system's stability, but it would create a far more dramatic and terrifying picture. It would mean that these 14 brilliant stars are living on borrowed time, their light and heat mere decorations around the ultimate cosmic predator, a darkness that holds their entire world in its grasp. This gravitational resonance creates pockets of temporary peace. Even in the 14-star maelstrom, astronomers have detected a faint, rhythmic pulse. The orbits of certain stars are locked together by simple mathematical ratios. For every 2 orbits one star completes, a nearby companion might complete exactly 3. This is an orbital resonance, a gravitational harmony that imposes a fragile order on the surrounding chaos. It acts like a cosmic metronome, coordinating the stellar dance to prevent catastrophic close encounters. The stars in resonance never get too close to one another, their paths synchronized by their mutual gravity in a way that minimizes their disruptive influence. This is not a permanent stability, but a temporary, beautiful truce in the gravitational war. We see a smaller-scale version of this in our own solar system. Neptune and Pluto are locked in a 3-to-2 resonance. For every 3 trips Neptune makes around the Sun, Pluto makes exactly 2. This gravitational agreement ensures that even though their orbits cross, they never collide, because Pluto is always in the safe part of its path when Neptune arrives at the intersection point. In the Quattuordecuple system, this principle is amplified to a staggering degree. A chain of these resonances could, in theory, link several of the stars together, creating a delicate gravitational latticework that holds a section of the system in a precarious balance. It is a cosmic clockwork built not from gears but from the fundamental forces of the universe, a fleeting symphony of order composed within an orchestra of chaos. How long can such a delicate arrangement last before the dissonance of the other stars shatters this temporary peace? The stellar cannibalism within this 14-star system creates cosmic zombies. These are not dead stars, but rather stars that have been violently skinned alive, their outer layers torn away to reveal the burning core beneath. Imagine a star that should be a brilliant, bloated red giant, but instead appears as a small, intensely hot and unnaturally blue object. This is a helium star, a stellar zombie. It is the exposed heart of what was once a much larger sun, now stripped of its hydrogen envelope by the gravitational greed of its companions. The process is one of slow, violent theft. In a tight binary pair, one star might expand as it ages, only to have its outer atmosphere siphoned off by the intense gravity of its partner. The donor star is left as a naked, helium-burning core, shining with a feverish, blue-white heat that betrays its traumatic past. Finding such a star in a Quattuordecuple system is like finding a murder weapon at a crime scene. It is direct, incontrovertible proof of stellar vampirism on a grand scale. The zombie star's existence tells a story of intimacy turned violent, of a stellar relationship so close and so destructive that one star was consumed not in a flash, but in a prolonged cosmic feast that left only its blazing skeleton behind. These objects are incredibly rare in the isolated cosmos, but here, in this gravitational pressure cooker, they are a natural byproduct of the constant crowding and chaos. They serve as permanent monuments to the system's brutal history, proving that in this family, even a star's own body is not safe from its siblings. Each star in this frantic dance betrays its secrets through a subtle, telltale wobble. When astronomers track a star's position with extreme precision, they sometimes find it does not move in a smooth, straight line. Instead, it traces a tiny, cyclical loop in the sky, a slight back and forth motion against the backdrop of more distant stars. This astrometric wobble is a gravitational confession. It means the star is not traveling alone. An unseen companion, something too dark or faint to see directly, is orbiting it. The star and its hidden partner are both actually orbiting a common center of gravity, a point that lies between them, causing the visible star to sway from side to side as it moves through space. In a simple system, this wobble is a clear signal. In a 14-star system, it becomes an interpretive nightmare. You are not looking for one wobble. You are trying to isolate 14 individual wobbles, each one caused by a different unseen companion, all overlapping and interfering with each other simultaneously. It is like trying to listen for the hum of a single bee in a swarm of 1,000, all buzzing at once. The gravitational signal from a massive planet yanking on one star gets mixed up with the signal from a faint brown dwarf orbiting another. A brown dwarf itself is a fascinating failed star, an object too massive to be a planet but not quite massive enough to ignite sustained fusion in its core. It simply glows faintly with the residual heat of its formation, a dark, cold ember in the cosmic night. Finding one of these hidden giants in the already crowded system is a monumental achievement. It requires scientists to build a fantastically complex model of the entire system, simulating the gravitational pull of every single visible star, and then looking for tiny, residual motions that the model cannot explain. Those leftover wiggles, those unexplained jitters in a star's path, are the fingerprints of the invisible. This painstaking process has revealed that some of these 14 star families harbor not just 14 suns, but also a hidden entourage of brown dwarfs and super-Jupiter planets, all adding their own quiet gravitational voices to the overwhelming stellar noise. It means the system is even more crowded than it first appears, its true population hidden in plain sight, revealed only by the delicate, persistent sway of the stars themselves. These 14 star systems are more than just cosmic oddities. They are living fossils, relics from a far more violent and crowded era in our galaxy's history. Galactic archaeology, the science of reconstructing the Milky Way's past, relies on finding such ancient survivors to piece together a story that has faded over billions of years. A Quattuordecuple system is a perfect, if rare, time capsule. Its very existence points to a specific set of conditions that were common in the galaxy's tumultuous youth but are almost unheard of today. The early Milky Way was a denser, more chaotic place. Immense clouds of primordial gas, rich with hydrogen and helium, collapsed with a ferocity we seldom witness now. It was within these extreme, high-pressure environments that the cascading fragmentation necessary to spawn 14 stars in one event was not just possible, but perhaps even routine. Finding one of these systems today is like stumbling upon a dinosaur bone in a modern forest. It is a direct, tangible link to a bygone epoch, a testament to a time when star formation was a more explosive and prolific process. By studying its intricate orbital architecture and the chemical composition of its stars, we can effectively read the environmental conditions of its birth. The specific ratios of heavy elements in their atmospheres, for instance, tell us about the composition of that original, ancient gas cloud. The complex gravitational dance reveals the density and turbulence of the stellar nursery that cradled them. Each piece of data is a clue, helping us write the biography of our own galaxy, revealing a past far more dramatic and crowded than the relatively serene cosmic neighborhood we inhabit today. This single, chaotic family of 14 suns is a window, allowing us to look back and witness the raw, untamed forces that built the Milky Way. This constant, shifting bath of starlight creates an environment where the chemistry of life faces an impossible barrier. Even if a planet, by some miracle, found a stable orbit within a temporary habitable zone, its atmosphere would be under constant assault by an invisible, sterilizing force. The real killer is not the heat or the cold, but the ultraviolet radiation pouring from multiple stars at once. A single hot, young star can emit enough UV light to break apart the delicate organic molecules that are the building blocks of life. Now amplify that by several such stars, all shining from different directions at varying intensities. The radiation environment becomes a chaotic, unpredictable storm. On such a world, complex molecules like amino acids or nucleic acids would be shredded almost as soon as they formed. It would be like trying to build a house of cards in the middle of a hurricane. The very foundations of biology, the long chains of carbon-based molecules that can store information and catalyze reactions, would be torn apart by photons carrying too much energy. There is no shelter from this. A planet's magnetic field might deflect some of the charged particles, but it cannot stop high-energy ultraviolet light. A thick atmosphere could help, but the same intense UV radiation would likely erode that atmosphere away over time, stripping it layer by layer until the surface is fully exposed. This transforms the concept of a habitable zone into a cruel joke. The region might technically have the right temperature for liquid water, but the water itself would be broken apart by radiation, and any complex chemistry in the water would be continuously dismantled. These systems are not just dynamically hostile, they are biologically barren, the ultimate deserts in the cosmos, where the fundamental rules of chemistry are rewritten into a recipe for permanent sterility. The search for life elsewhere often fills us with hope, but here, in the 14-star crucible, the universe seems to have designed a perfect machine for preventing it. The final act of this 14-star family is a galactic fireworks show of unparalleled scale. There will be no gentle drifting apart, no quiet fading into the dark. The system's inherent instability guarantees a spectacular end, a gravitational demolition derby that will scatter its components across the galaxy. The first sign of the end times will be a sudden, violent ejection. One star, after a millennia of close passes, will finally receive the perfect gravitational slingshot. It will be catapulted outwards, not just leaving the system, but achieving escape velocity from the Milky Way itself, destined to wander the intergalactic void for all eternity. Its departure will be the first domino to fall, upsetting the fragile balance that held the remaining 13 stars together. Chaos will rapidly escalate. Without that one star's gravitational influence, orbits that were once manageable become wildly unstable. Close encounters, once rare, become the norm. Two stars on intersecting paths will no longer narrowly miss. They will collide. The merger of two suns is not a gentle coming together. It is a cataclysmic release of energy, a temporary new sun that outshines the rest of the system combined, forging a heavier, more unstable star in a flash of cosmic violence. This new, more massive star lives a short, furious life, burning through its fuel in mere millions of years before exploding as a supernova. Its death throes send a devastating shockwave through the already reeling system. This blast wave does not travel through empty space. It slams into the atmospheres of nearby stars, stripping them bare, compressing their cores, and potentially triggering more premature supernova in a chain reaction of stellar death. The core of the system becomes a vision of hell, a continuous strobe of detonating suns. For a brief, brilliant period, this single point in the galaxy will be one of the brightest objects in the sky, a beacon of destruction visible from countless light years away. When the last supernova fades, the silence that follows is profound. The brilliant family of 14 suns is gone. In its place, a grim graveyard remains. A few lone, scarred stars, survivors of the apocalypse, are sent careening away on new, lonely trajectories. The rest of the system is now a collection of dark, dense remnants. Neutron stars, the ultra-dense cores of the exploded giants, spin wildly, emitting pulses of radiation. And at the very center, if the most massive stars met their end, a small cluster of black holes may now orbit one another, their invisible gravitational dance the only legacy of the light that once was. The 14-star system completes its life cycle not with a whimper, but in a symphony of bangs, its material scattered to become the building blocks for future stars and planets in the endless cycle of the cosmos. 30 suns, all bound in a gravitational tapestry of chaos and creation, reveal a universe far stranger than we ever dreamed. From the orbital roller coasters that shatter the concept of a stable planet to the stellar cannibalism that forges cosmic zombies, each discovery peels back a layer of cosmic reality. We have witnessed systems that are factories for gravitational waves. They hum a silent song of warped space-time and graveyards of ancient black holes, the dark remnants of a violent past. These Quattuordecuple families are not just astronomical curiosities. They are extreme physics laboratories pushing our understanding of gravity, magnetism, and stellar evolution to the absolute breaking point. They are living fossils whispering secrets of the galaxy's violent youth and temporary monuments to an order that is always on the verge of collapsing into spectacular ruin. Their very existence challenges the clockwork elegance we once assigned to the heavens, replacing it with a beautiful, terrifying, and fundamentally unpredictable dance. So, as we conclude this journey to the edge of understanding, we turn the question over to you. Which of these 30 truths about 14 star systems boggles your mind the most? Was it the fractured, multi-colored shadows on a hypothetical world, or the prisoner star on its million-year orbit? Share your most astonishing thought in the comments below, and if you crave more voyages to the frontiers of cosmic mystery, subscribe for the next journey into the unknown.